Good morning, everybody. My name is Chris Valicka. I'm from Sandia National Laboratories, Department of Energy Lab out of New Mexico. And this is some joint work I did with Scott Mitchell, Stephen Rowe, Simon Zoe, as kind of an internal research and development project. Let me get right to it here. So here's my brief overview, pretty typical structure. I'll talk a little bit about our motivations and some related areas. And then I'll kind of try and give a high-level overview of the algorithm. There's not enough time to go into details. My hope is just to kind of give you a sense of what we're doing and get some feedback from you all if there's time during the questions session. And talk about some next steps and how it relates to some other research we did under this internal research and development project. Okay, so we kind of classified our problem as a planning problem or optimization of spatial coverage, right? So I've seen a lot of talks on a variety of these subjects here today. So we're kind of focusing on Earth-observing sensors, right? So this could be a spaceborne sensor or an airborne sensor. And it differs a little bit from some of the path planning problems, a variety of path planning problems, and hopefully that'll become clearer as I talk through things. But there's some nice rigidity in aircraft orbits or spacecraft orbits that you can exploit for your planning problems that make them a little bit more certain, I guess, is one way to describe it. But in general, some of the optimization of spatial coverage techniques we looked at were applied in these different domains, and hopefully those will become a little bit clearer as I show you some of the pictures later in the talk. So I put together this quasi-tree. It's kind of more of a graph. It's not a very strict ordering here, but maybe what's something that's a little bit different about our approach is that we draw pretty heavily from computational geometry. So Scott Mitchell is a world-class kind of researcher in computational geometry. So we stood on his shoulders to help formulate our problem. So in the broader scheme of computational geometry as it relates to planning, we kind of specify our problem a little more specifically, right? So we're kind of interested in a polygonal target, right? So there are techniques that are specialized for certain shapes and certain types of geometries, but we're trying to be a little bit broad. So you can imagine taking images of the Earth in a variety of different places according to a variety of different constraints. So we wanted to have a broad or general technique. And then as you move down this quasi-tree graph thing here, you can see there's a variety of different types of techniques, right? So let me see here. So, oh, nice. Okay. In many cases, there are footprint-specific heuristics, right? So if you know your sensor's field of view really well, you can perhaps exploit that to find a very useful heuristic if you're trying to cover a region of interest. Some of the other techniques which are related to the one we implement here, are subdivision with recursion. This is quite popular. Shifting techniques, this is something that we saw in a lot of the computational geometry literature. I would say that ours kind of fits more into a relaxation technique, and that again will become clearer as we move along here. Just for a little bit more specificity, sometimes we found papers and nice work done under this subdivision with recursion kind of approach to solving problems that were specialized for circular footprints or polygonal footprints. We tried to be general, so we didn't make very strong assumptions on what the sensor field of view looks like. And if you're a satellite in space and you're looking at the Earth at a weird angle, your footprint might take on a very weird shape. So we wanted to try and accommodate that type of problem. Okay, so some more details about our spatial coverage problem. So we kind of restricted ourselves to what I would call smaller placement problems, if you will. So the assumption is somebody requests some science over the United States, or Google requests some exquisite map over the United States, but in general, an aircraft with an onboard sensor can probably image that region of interest with on the order of 10 to maybe 100. That would be a larger scale instance of our problem. So, it's somewhere on the Earth, right? I guess you could imagine Mars orbiting platforms doing something similar too, but in general, we're kind of focusing on Earth-observing sensors. What else do I have here? So yes, one key criteria that we kind of picked up from some of the application specialists we spoke with was, in general, they don't like to have gaps in their Mosaic images, right? So if I'm going to stitch all these images together, I want to make sure that I don't miss a part of the U.S., or I don't want to miss part of a forest fire I'm trying to monitor, or I don't want to miss some extent of the river I'm trying to take all these images of. So that's a constraint that'll be folded into our problem here. I already alluded to the fact that our region of interest, ROI here, it's kind of this polygon in the black line in the bottom of the chart here. It's modeled as a polygon. Sometimes there can be holes. We wanted to try and be general. So if, for example, you wanted to take a picture of an entire city, but you wanted to avoid certain parts of the city, or if you wanted to take a picture of a certain area and avoid a certain area, you could have a hole in your region of interest. Some other kind of loose assumptions. We in general kind of focused on footprints that are kind of nearly convex and have good aspect ratios. We didn't really explore situations where you have some really weird geometries. So hopefully that'll be also clear in some of the pictures I have coming up here. Okay, so high-level overview of what we're doing in this space, right? So think of a spatial optimization problem, right? So we have our region of interest, we have our sensor footprint we have selected, and the goal is to kind of cover that region of interest with as few number of sensor footprints as possible. So what we're doing at the end of the day is we're taking what is a continuous problem. So you can imagine a number of different types of discretizations of that coverage space, and a number of different types of footprints, places you could point your camera if you wanted. And we're taking a continuum of that problem and we're discretizing it. So we have two discretized sets here. So a set of coverage points we need to cover, and a number of footprint placement points where we could potentially place the sensor. And then we take those points and the geometric relationships of those points, and we stick it into a mixed integer linear program, right? So we have some objective, use the minimum number of sensor images as possible according to some constraints. And let me get into a little more specifics here. So we drew heavily upon a method that's used in some of the disk shifting algorithms. So if you have this annulus, this rectangular square here with a big hole in the middle, we've got kind of two flows. In the top flow here, we're generating our coverage points, right? So recursively, we're throwing darts, if you will. There's a paper we reference where they talk about sampling this space as throwing darts. But anyway, we recursively place these coverage points according to the criteria that for every coverage point we put down within our area to be covered, the next point has to be at least some epsilon distance away. And so we do this until the entire space can be covered with our points, and every point is at least epsilon points away. We do something similar for replacement points. These things don't necessarily have to use the same parameters, but we've kind of found it useful to use the same epsilon parameter when we sample. And depending on the epsilon parameter you choose, you can have a much larger or much smaller problem, resulting in a different number of placed images, if you will. So we take these two pre-processing steps. We take some notion of the geometry of the sensor footprint, and we put them in this metaphorical funnel here, and we come up with our mixed integer program. So here we are, obligatory math slide. We kind of had three instantiations of this problem. So equation one is a basic coverage problem. So the goal here is just minimize the number of footprints, minimize the number of camera images taken, subject to the fact that every coverage point has to be covered in a region of interest. So that's equation one. I'll have some pictures on the next slide that explain things. There are also some nomenclature details down there at the bottom for those who are interested. The second instantiation here, we wanted to try and penalize overlap, right? So some notion of overlap is good. In general, sensors at the periphery are less performant than they are in the center of the field of view. So sometimes you want to have additional pixel data, if you will, on the boundaries. And so some overlap is good. We found with equation two, though, this kind of caused some undesirable behaviors. So we also added in equation three this notion of rewarding efficiency. So in equation two, it's almost like a minimax, right? So you're trying to minimize the number of placed images, but in reality, now you're rewarding overlap, so you're getting additional images. So we tried to reward efficiency, and there's a number of different ways to do this, and there's a little bit more detail in the paper of exactly how we did that, but here's kind of our objective function with some small modifications of the constraints and additions of decision variables there. So maybe this is a better slide to kind of talk through things, right? So to describe the pictures, I got some more pictures coming up here on the next few slides. So in the bottom, your bottom left here, we have a placed footprint in this annulus, this rectangle with a hole in the middle, right? And each one of the crosses is a potential placement point, and each one of the x's is a potential coverage point, right? So you have to cover all of the x's in a solution, right? And what we do in the pre-processing step is we shrink the footprint, right? So this green circle here for the radius is the actual dimension of our footprint, right? But we assume when we go and solve our problem that the radius is actually a little bit smaller, so we can, because we've discretized the continuous space, we want to make sure that we don't actually miss some spot that is in the region of interest but not covered by a coverage point. Anyway, the next picture here is just to say, we wanted to penalize overlap a little bit here, right? So we're trying to push the footprints a little bit further away, right? But we're getting some behavior where they're going towards the boundaries. So we reward efficiency, and that kind of ends up pushing these placements back in. So maybe a few examples. So we looked at a couple of kind of I'll call them canonical, but they're goofy shapes, right? So this polygon here with the hole in the middle is something we borrowed from another woman's paper. She was looking at coverage of the U.S. via radar systems, but she called the shape the moped shape. Anyway, we tried covering it with a variety of different footprints. You can see the triangles there in the bottom, some squares in the middle, and then circles at the top. You can also see the space sampled according to coverage and placement points in the first two columns, and then the resultant solution in the final column. And then we had another imaginary shape we put up here with some peculiarities. And then you can see in the bottom right here, kind of maybe a more realistic sensor footprint as it is projected from space onto the Earth for a variety of different things. So that was a lot of fun, and it was interesting to kind of explore some of the nuances of these different shapes under this paradigm. So just a little more detail on what we actually ended up using. So at Sandia, we take pride in computing, so we call a 64-core half-terabyte system a workstation as opposed to a server. But that's kind of the metal we had to use. So we had both an open source academic license Rowe solver, which was quite performant, and the Cplex commercial solver. I don't have any details comparing their performances, but we were able to solve using both of those types of solvers. All the software we use to produce these results is available on GitHub if anybody's interested in picking that up. That's there today. A little more detail, some of the pre-processing steps are all done in C++, and then we make use of Python and Pyomo, which is a Sandia-developed algebraic modeling language for optimization problems. We use that to formulate our problem and then generate the LP or mixed integer LP and pass that on to pick your solver of choice. And then on the far right here, we kind of did thanks to some of the reviewer comments, we did a little bit of an exploration of our main parameter epsilon and its effect on runtime and number of sample points and things like that, as well as the resultant number of footprints placed for the example at the top of the page. So I'm hoping there's follow-on work for this type of thing. I'll just say a couple things real quickly. The hope in this research was to kind of look at general satellite or sensor scheduling problems, and this was one instantiation of a problem we looked at. We have two other papers out that I can point you to, which are kind of alterations of this problem. They all use mixed integer linear programming under the hood, but they kind of consider different instantiations of this space. The hope was to have the problem I presented today as a sub-problem in a larger scheduling problem, explore some of the nuances there. And so future work would be connecting this up to some of the other papers, some of the other research we've done. I saw some other good talks on related problems here at this year's ICAPS conference, and there are other colleagues here looking at some of these things that we want to look at next, specifically when sensor slew times or the rate of the orbit is such that the footprint kind of shapes over the duration of the collection window, so that when you start taking the image of your region of interest, your sensor field of view looks like one polygon, but when you get to the end of the region of interest, your field of view changes a little bit. So we have some thoughts on that, and that's some work we'd like to get into later on. I think that's all I got. Happy to take questions.
Questions? Okay, so one here and one. Okay.
So for visual imagery, cloud cover is often an issue. And I can imagine that your choice of footprints would impact how many attempts it might take you to actually get clear imaging of the region you were interested in. Did you consider that issue at all?
Good question. Yeah, thank you. So in this formulation, no, we did not consider cloud cover. We did consider gaps, right? But I think that doesn't quite cover exactly what you're talking about. I think if we start to consider a little bit more complex versions of this problem, we would like to roll something like that in. Certainly in the other scheduling papers we talked about, we specifically addressed that, but it wasn't really for this instantiation of the problem. So I agree, cloud cover is an absolute issue. I'd be interested in your thoughts or other thoughts on how to maybe roll that into this formulation or similar formulations.
So thanks for the talk. It was really inspiring. So one question is that when you were doing this discretization of the locations, have you considered those discrete points having different importance for coverage? For instance, if it's a city center, it may require higher coverage than suburbs.
Yeah, so great question. It's something we have thought about. I don't have any implementations that directly address it, but we did do some kind of thoughts about how we might introduce priority, if you will, into these different coverage points, or uncertainty into these different coverage points, right? So that maybe would speak a little bit to the cloud coverage, but not quite again. Anyway, not implemented. I'd be happy to talk more offline about that, but absolutely, I think it's relevant to the problem space.
It can be, I believe, just to comment, it can be easily solved with a soft constraint, maybe. Just
Thank you.
Thanks.
Okay. One more question here.
Your problems are very homogeneous in the sense that your shape is the same shape that you want to cover every time, and your footprint is the same footprint that you want to use to cover every time. If you're in a low Earth observing setting, that's clearly not going to be the case if you have strange orbits. And, similar to Date's question about cloud cover, the clouds are going to change as well. So there seem to be some natural ways to sort of evolve what you've done, to say my shape is evolving, my footprint's evolving, but do you have other thoughts about that?
I'd be interested to talk with you more about that. The most thought we've given to it to date is, hey, how do we drive down the computation time on this specific instantiation so that we could try iterations or similar types of polygons with slight alterations or slight alterations to the footprint shape, or combinations of the two, right? So that I could solve those fast enough and then have a lookup table, if you will, to kind of cover the space of how does my shape evolve over time. What are the nuances, or what are the kind of range of footprint placements, and how do things change? But all the while having kind of answers for some subsets of those types of changes.
Any more questions? All right, so let's move on to the final talk. Let's give the